Hello, we are going to talk about Gauss law. Gauss law in electrostatics, it states that electric flux through any closed surface is 1 upon epsilon naught times the charge enclosed by the closed surface. Mathematically, it is given as phi equal to closed integral of E dot ds. Remember, we have taken double integral because integration is over entire area, over the closed surface of area. Suppose there is a charge Q which is enclosed by a closed surface, then electric flux is given by 1 upon epsilon naught times the charge enclosed by the closed surface. And on this basis, we are going to calculate flux through the surface of a cube. Suppose a cube encloses a charge capital Q within its center. Then what would be the flux through each surface? So electric flux through entire cube through all the 6 faces is given by Q upon epsilon naught. Thus, the electric flux through each face would be 1 by 6 times Q upon epsilon naught. Right? Yes. Now, see in this figure. Suppose there is a charge Q which is placed at origin. Then in that case, what would be the flux through each face? See clearly. How many cubes are required to enclose this charge completely? If you notice, then 4 cubes up and 4 cubes down, that is in total 8 cubes can enclose this charge completely within it. So flux through 8 cube would be Q upon epsilon naught. Thus flux through each cube would be 1 by 8 times Q upon epsilon naught, and hence flux through each surface of the cube would be 1 by 48 times Q upon epsilon naught. So, let's talk about application of Gauss law to find electric field for symmetric charge distribution. First is spherical symmetric charge distribution. So, what are the conditions to use Gauss law? First condition is that obviously charge should be distributed over the surface and rho should be either a function of r or it should be constant. So, see in the figure nicely. Suppose there is a sphere and the charge is distributed over it. Now, if we place 4 observers in the 4 sides as shown in figure, then all would see the same amount of charge. Thus, it has spherical symmetry. So, what should be the electric field due to the uniform charge carrying sphere at an inside point? So, applying Gauss law, closed integral of E dot ds equal to Q enclosed by epsilon naught. So, E into what is with the area? E into 4 pi r square. If you take a Gaussian surface of radius small r within the sphere of radius capital R, then E into 4 pi r square equal to 1 upon epsilon naught times Q can be written as density into volume. So rho naught into 4 by 3 pi r cube. Upon solving, we get E equal to rho naught r by 3 epsilon naught into r cap. Remember, electric field would point radially outward and it is directly proportional to. Now, what should be the electric field at outside point? So for this, consider a sphere of radius capital R and the charge density is rho equal to rho naught. So charge is distributed over the surface and rho equal to rho naught. So it has got spherical symmetry. Thus, applying Gauss law, let's draw a Gaussian surface of radius small r greater than capital R. Applying Gauss law, we get E dot ds equal to q enclosed by epsilon naught E into 4 pi r square equal to 1 by epsilon naught rho naught into 4 by 3 pi capital R cube into r cap. Remember, here the volume would be taken as 4 by 3 pi r cube because charge is distributed till the sphere only, till the sphere of radius capital R only, right? So we will take rho naught into 4 by 3 pi capital R cube. So upon solving we get E equal to rho naught R cube by 3 epsilon naught into R square R cap. So if you draw the graph E versus R for the electric field of a uniformly charged sphere, so E is directly proportional to R for small r less than capital R, and this has maximum value at small r equal to capital R, and outside the sphere electric field is inversely proportional to R square, right? Now we use Gauss law to calculate electric field in other cases too. For example, suppose there is a charge distribution as rho equal to rho naught into 1 minus r by r for r less than capital R, and this is equal to 0 for r greater than capital R, it should be here. So once again we can see that charge is distributed, so and r rho is a function of r, so spherical symmetry, so we can apply Gauss law here. So first we will calculate electric field for inside point. So for inside point we draw a Gaussian surface. So you can see that applying Gauss law we get E dot ds equal to q enclosed by epsilon naught. So E into 4 pi r square equal to 1 by epsilon naught, and q can be written as charge density into volume. So rho naught into 1 minus r by r into 4 by 3 pi r cube r cap. So 4. So upon further solving we get E equal to 1 by 3 epsilon naught into rho naught into 1 minus small r by capital R, small r by capital R into small r, and once again it is pointing radially outward. Now similarly for outside point we get E dot ds equal to q enclosed by epsilon naught. So E into 4 pi r square equal to 1 by epsilon naught. Now remember here, see it very nicely. Many people can see that outside electric field would be 0, rather charge would be 0 because density is 0 for r greater than 0. But this is very important here. Density is 0 outside, but for calculating electric field outside, we will consider the charge density up to capital R, and up to r equal to capital R, charge density is not 0. That has value rho naught into 1 minus small r by capital R. So calculating that, we get E into 4 pi small r square equal to 1 by epsilon naught integration 0 to capital R rho naught into 1 minus r by r into 4 pi r square dr, and upon solving we get rho naught r cube by 12 epsilon naught r square r cap. Now let's talk about electric field due to thin spherical cell. So consider a thin spherical cell of radius capital R we wish to find electric field at any point inside it. So we draw a Gaussian surface of radius small r. Remember, charge density is sigma equal to dq by ds. So applying Gauss law for inside point, we get closed integral of E dot ds equal to q enclosed by epsilon naught. Now since it is a thin spherical cell, so it is hollow, so inside electric charge equal to 0, so E equal to 0. For outside point, let's consider a Gaussian surface of radius small r, this time greater than capital R, and applying Gauss law, we get E dot ds equal to q enclosed by epsilon naught. Now E into 4 pi r square equal to q by epsilon naught. So we get E equal to q upon 4 pi epsilon naught r square r cap. So for outside point, electric field behaves as if entire charge is concentrated at the center. Now let's talk about electric field due to a thick spherical cell. Consider a thick spherical cell of radius, inner radius small a, outer radius small b. Now for inside point, once again you can draw a Gaussian surface. Electric field would be 0 for r greater than a but less than b. Let's draw a Gaussian surface of radius small r. So we'll take E dot ds equal to q enclosed by epsilon naught, and upon solving we get E into 4 pi r square equal to 1 by epsilon naught integration from a to small r rho naught r into 4 pi r square dr, and upon solving we get rho naught upon epsilon naught r square minus a to the power 4 by r square into r. Now for r greater than b, once again draw a Gaussian surface of radius small r greater than b. So applying Gauss law, E dot ds equal to q upon enclosed by epsilon naught. So we get E into 4 pi r square equal to 1 by epsilon naught integration from a to b rho naught r into 4 pi r square dr. Upon solving we get rho naught upon 4 pi epsilon naught r square b to the power 4 minus a to the power 4 into r. Now there is a very important question which we will solve based on Gauss law. Suppose there is a concentric spherical cell. Suppose there is a concentric spherical cell of different radii, such as innermost radii is A, then the radius is B, then the outermost radius is C. So let's find electric field at any point inside the sphere of radius small a. So we draw a Gaussian surface of radius small r less than a. So electric field would be 0 because no charge is enclosed in that region. Now for r between a and b, applying Gauss law, we get E into 4 pi r square equal to charge enclosed is q1 by epsilon naught. So we get E equal to 1 upon 4 pi epsilon naught q1 by r square into r. For r between b and c, applying Gauss law, E into 4 pi r square equal to 1 by epsilon naught q1 plus q2. So E equal to 1 upon 4 pi epsilon naught q1 plus q2 by r square into r. For r greater than c, E equal to 1 upon 4 pi epsilon naught q1 plus q2 plus q3 by r square into r. So that's how we will be calculating, we will be using Gauss law to calculate the electric field. Now let's talk about electric field in the cavity inside a uniform charge carrying solid sphere. Suppose there is a uniform charge carrying solid sphere of density rho naught. Radius of the sphere is capital R and there is a cavity within the sphere, and we wish to find electric field inside this cavity and outside this cavity. So first, how will we be doing this? So let's first calculate for inside portion. Consider a charge carrying uniform sphere of radius capital R, and there is a cavity. So how will we do this? So first, let's consider that there is no cavity. Then what would be the electric field at point P inside the sphere? We know that electric field at any point inside the sphere, uniformly charged sphere, we have calculated today, and it comes out to be rho naught r by 3 epsilon naught r cap. You can see it inside point we have calculated. So rho naught r by 3 epsilon naught into r cap. So on the similar analogy, we get rho naught r by 3 epsilon naught into r cap, and that we can write in form of vector as rho naught by 3 epsilon naught into OP vector. Now consider there is only cavity having charge, negative charge density. Remember there was cavity, but then too we have considered entire sphere. That means we have added extra portion there. So this time we will subtract that, and for subtracting what will we do is that we will consider the negative charge over there. So due to the negative charge density, electric field at point P would be E2 equal to minus rho naught by 3 epsilon naught into O dash P vector. So net electric field would be sum of E1 and E2. So it is rho naught by 3 epsilon naught OP vector minus O dash P vector. That comes out to be O dash vector. Thus, inside the cavity there is a electric field, and that is uniform. For outside portion, we know that electric field outside it is given by, we have that also calculated. So it comes out to be rho naught by 3 epsilon naught r cube by r square into r cap. So here we will draw a Gaussian surface of radius small r. So electric field due to the sphere without the cavity portion would be rho naught r1 cube rho naught r1 cube by 3 epsilon naught r square r cap, and electric field only due to the negative charge density over there, it would be rho naught by 3 epsilon naught r1 cube into r square. So that would be the electric field due to the negative charge, and hence the net electric field would be the sum of E1 and E2, and that comes out to be rho naught by 3 epsilon naught r1 cube upon OP cube into OP vector minus r2 cube upon OP cube into O dash P vector. So that's all for today. In the next class we will see some other problems.